All right, welcome back. Math 1920, Calculus 2. We're in Chapter 5, Section 2, learning how to differentiate the natural log function. All right, so Theorem 5.5, we're going to use the log rule for integration. Okay, so let u be a differentiable function of x. So if we get the integral of 1 over x dx, okay, that gives us the natural log of absolute value of x plus c, or if we're going to be doing u-substitution, we have the integral of 1 over u du, that's going to equal the natural log of absolute value of c, or natural value of u plus c. Okay, so if we look at the differentiation rules, which we did in the last chapter, or last section, okay, we're going to use those kind of backwards here when we do the integration piece. Okay, so if I give you this integral, we have 2 over x dx, okay, and we rewrite that because we can pull that 2 out because it's a constant. So we're going to get 2 times the integral of 1 over x dx, okay, using our theorem. When we do the integration, all right, the integral of 1 over x translates into natural log of absolute value of x. So when we do this full integral here, it becomes 2, that's that constant out in front, times natural log of absolute value of x plus c. All right, it does get more complicated than this when we do this. However, we are able to rewrite this one if and only if we have an even power out in front. Okay, so because we have to maintain the absolute value of the natural log of x there, all right, if we have an even power, 2, 4, 6, 8, 10, and so on and so forth, we can use the property of logs and bring that power back up and rewrite this specific one as natural log of quantity x squared plus c. It's just because an even power, whatever we put in there, will never be negative. Okay, so that's what helps us rewrite that using the property of logs. All right, let's do another example here. We have the integral of 1 over 4x minus 1 dx. All right, we're going to practice using u-substitution. When we are applying natural logs, we always want to make sure that we choose u to be something in the denominator, okay, when we do these problems. So let u equal 4x minus 1 here. Okay, so then du becomes 4 dx. Okay? Now, we don't have a 4 dx, but we have a 1 dx, so we have to replace that or rewrite it. Okay, so we can rewrite it as du over 4 is equal to dx in this case. All right, so now we can replace dx, all right, and rewrite our integral. So we replace it and write everything in terms of u. So we have the integral of 1 over u times du over 4. We're going to pull that 1/4 out in front of the integral because it's a constant. So we have 1/4 times the integral of du over u. Remember, du and u prime are interchangeable for these problems when we write them out. Now when we do the integration, we apply the theorem. So this becomes 1/4 natural log of absolute value of u plus c. Don't forget the plus c. And then we have to replace u with what we pulled it out for in the beginning. So we end up with 1/4 natural log of 4x minus 1 plus c. And remember, don't forget the plus c because these are indefinite integrals. If we had limits of integration, then we would evaluate them out. All right, next example. We want to do the integral of 3x squared plus 1 dx divided by x cubed plus x. So let u be the denominator, all right? So u is going to be x cubed plus x. And then du is going to be 3x squared plus 1 all times dx. I forgot to write the dx in there. But know that that 3x squared plus 1 is all multiplied by dx, so we can do direct substitution here. So choosing u to be x cubed plus x, when we take du, it actually lets us replace the entire numerator with just du. Okay, so we can rewrite this integral as 1 over u times du, right? We're rewriting this integral all in terms of u when we do this. All right, so it breaks it down and lets us simplify this down. This becomes the natural log of absolute value of u plus c, just using the theorem, right? And then we have to replace u with what we pulled it out to be originally, so we end up with natural log absolute value of x cubed plus x plus c. Okay. Another example here, a little bit more complicated on this one. Okay. We have the integral of 2x divided by x plus 1 quantity squared dx. Okay, so we're going to do some u substitution. Careful when you choose u as the denominator here. Choose the u to be what's in parentheses. Okay, so we're going to let u equal x plus 1. Okay, so du equals dx here. Okay, now that does not allow us to do some substitution that we need to, all right? There's still a 2x in this equation, even if we were to try and rewrite this all in terms of u. So the method approach here, okay, is you have to take our u equation, u equals x plus 1, and solve it for x. Okay, so when we solve u equals x plus 1 for x, we get u minus 1. So now we can replace x with its u equivalency. So now we can rewrite the integral. Okay, the 2 stays there. We replace x with u minus 1. Okay, and then it's over u squared du. All right, so we've replaced everything now. So sometimes the methodology is you have to write x in terms of u as well. Okay, just a couple more steps when we do that. Okay, so when we rewrite this integral, just cleaning it up, making it look a little better, it's 2 times the integral of u minus 1 divided by u squared du. Okay, so the methodology here now is, since they have a common denominator, okay, we can write this as 2 separate integrals. Okay, so this becomes 2 times, now I'm putting brackets because it's still got to multiply to both integrals here. And if I rewrite the integral with a common denominator, I can break it into its 2 parts. I get the integral of u over u squared du minus the integral of 1 over u squared du. Okay, so we're separating that into 2 separate fractions. Okay, now we simplify and rewrite those integrals so that we can do the integration. The u over u squared becomes 1 over u. Okay, and then we rewrite the 1 over u squared as u to the minus 2. Okay, so this is what we get here. We get 2, okay, times the quantity of the integral of 1 over u du minus the integral of u to the minus 2 du. We know how to do all of these integrals now. So we're going to still have that 2 in front. The integral of 1 over u du becomes natural log of absolute value of u minus the integral, all right, we got to undo the the power rule here, u to the negative 2 becomes u to the negative 1 divided by negative 1. Make sure we're really keeping track of signs here, all right, plus c. All right, just simplifying that down, taking care of the negative step there and rewriting the u. Okay, so u to the minus 1 we rewrite as 1 over u, and then negative over negative becomes a plus sign then when we do this. We end up with 2, okay, times the quantity of the natural log of u plus 1 over u plus c. Okay, now we replace u with what we pulled it out with before. Okay, so we get 2 times the natural log of absolute value of x plus 1 plus 1 over x plus 1 times c. Okay, and then we can distribute the 2 through for our final answer as we go through there. Okay, so one of the more complicated ones where we kind of got to do a double substitution type scenario. Okay, now sometimes we have other ones where we have the numerator has a greater degree than the denominator. Okay, that can impose a problem on us sometimes. So in example 5, we have to maybe do some long division first when we do this one. Okay, so if the numerator has an exponent that's the same as the denominator or greater than the denominator, we're going to have to do some simplifying first, because if we choose u here to be the x squared plus 1, when we do our du, all right, we're going to lose a power or an exponent down, and we won't be able to cancel out the numerator. So a simple step here is to do long division first and foremost. Sometimes it's easier if you factor the numerator and denominator and cancel out some binomials as well. So that's another method to it. But if you can't factor things out nicely, right, can't really factor x squared plus x plus 1 nicely, all right, to cancel things out. So we have to use long division in this case. So when we do our long division, we get 1 plus x divided by x squared plus 1. Remember, that's our remainder, x over x squared plus 1 in our long division. Okay, now we can set up our integrals. So we can rewrite the integral, okay, as 1 plus x over x squared plus 1 dx. Now we know perfectly well how to do our integration of that piece, okay? We break it into two separate integrals, right? So the first one, I'm going to step back a slide. Okay, so you can see we're going to integrate 1. So we have the integral of 1 plus the integral of x over x squared plus 1 dx. So we're going to do that, and we're going to pull out a 1/2 out of the denominator, or 2 out of the denominator, essentially. Okay, and then rewrite these. Now we integrate. The integral of dx is x plus, we have 1/2 natural log of x squared plus 1 plus c. All right, we chose u to be the x squared plus 1. Okay, I didn't show the u-substitution step here. U is x squared plus 1, du is 2x dx. Okay, so we replaced that and did the integral. So see the last 3 examples have how to do the u-substitution piece on that one. Okay, but when it works out, that's what our final answer would be. Okay, and you can always check your answer by taking the derivative of the function that you got an answer of. Okay, now write all these down. So these are just general guidelines that your book goes through in order for you to be able to take the integration or the integral of anything and apply the natural log to it. All right, so let's say we want to solve the differential now. Okay, this one gets a little bit more complicated. Notice it's dy over dx equals 1 over x natural log of x. So this is going to be a multi-step problem here. Okay, and this is probably as challenging, I guess, as they would get in this section. So we can rewrite it first. Okay, so dy over dx, okay, is equal to 1 over x natural log of x. We can rewrite this as dy equals dx over x natural log of x. If we integrate dy, we just get y. Okay, so that's why we can do that. We're going to take the integral of both sides of the equation. So move the dx first, integrate both sides. Know that when we integrate dy, okay, it's just the integral of 1 in terms of y, so we get y back. So that's why we can rewrite this as y equals the integral of 1 over x dx. Okay, now we should be able to recognize that there is a log rule, kind of in there. So, how we choose u is very important here. Okay, there's a couple choices we could make. We could make u equals x, doesn't substitute in right. We got to make sure that we get in the right form when we do this. Okay, so we can also divide the numerator and the denominator by x. Okay, simplifying things down here. Okay, so that gets us into our u prime over u, right? We know if we took the derivative of natural log of x, we get 1 over x. So in this case, u is going to equal natural log of x. Okay, du is going to equal 1 over x dx. So we can do our direct replacement now when we do that. So it just ends up giving us the natural log of absolute value of u plus c. Okay, so just note that if we let u equal natural log of x, du equals 1 over x dx. Okay, and we're replacing the 1 over x dx with du. Okay, and then we'll have 1 over u. And then last part, right, replace u with what we chose it to be. So we have natural log of the absolute value of natural log of x plus c when we do that. Okay? Don't forget the plus c because we're dealing with indefinite integrals. Okay. We're going to do I'll do some of the other trig functions in class so you can derive where they come from as well. But just know, if we are able to rewrite these, they work out easier. Okay, so we want to find the integral of tangent of x dx. So the first approach in this, right, we're looking for something, through our properties and things like that. But most of our properties only deal with if we have something like secant squared or tangent squared or things like that, not necessarily the original function. Okay, so one way to derive this in, anytime we have a cotangent or a tangent or a secant or a cosecant, always try to rewrite everything in terms of sines and cosines, all right? Get back to basics. So if we rewrite tangent of x in terms of sines and cosines, all right, it becomes the integral of sine of x over cosine of x dx. Now we got something working here. We can use natural logs. So for us, all right, choose u to be cosine of x. That means du is going to be negative sine x dx. We can replace all of that, right? We just have to make sure we carry through the negative piece here, okay? So where that comes out, okay, in front. So if u equals cosine of x, du equals negative sine x dx. And then we have what? Our du over u scenario that we're able to integrate, right? Or write it as u prime over u. So now we do our integration, and we end up with negative natural log of absolute value of u plus c, and then we replace u with what we chose it to be, all right, which is cosine of x. So our final answer is negative natural log cosine of, or negative natural log absolute value of cosine of x plus c. So that's how we integrate tangent of x, okay? We've gone through some of these before, okay? So basic integrals, make sure that you have all these written down. So when you're doing integration, you get to this part, all right, you're able to simplify it down. You can just use the table here to finish the integration for you. Okay, and we'll derive the rest in class. I'll do cotangent, we'll do secant, and we'll do cosecant as an example in class. All right, well, that's the end of 5.2 lecture. We'll be going through some more of these in class, but if you have any questions, feel free to email me. Else, have a great day. I'll see you in class.